afternoon, Chairperson of AEC 2022, Professor Chen Zhijie, my old classmate and good friend from School of Public Health, NTU, and dear participants online up in the cyberspace, mostly in Southeast Asia, and young participants who sit in this nice aircon auditorium. Okay. This is a very special symposium on aerosol and air pollution in Southeast Asia. We are very honored to have 4 invited speakers from Chiang Mai, Thailand, from Selangor, Malaysia, Surabaya, Indonesia, as well as Kansas City, near Mekong Delta. Okay. As we know, Southeast Asia is one of the fastest growing regions in the world in terms of industrial development as well as economic growth. As such, air pollution is a challenging and emerging issue that no one can avoid. As we know, that air pollution is never a local or national issue. Rather, it's a regional or global issue. For example, living in Taiwan, actually we receive air pollutants in winter all the way to from the north, China and Mongolia. And in springtime, actually we receive air pollutants from biomass burning, mostly from Southeast Asia. That's why sometimes I told my students from Vietnam and Indonesia, whenever you miss home, perhaps you just breathe harder and then you could smell home. So that also underlines the importance for multinational regional collaboration. Okay, so I hope this special symposium is a very good beginning, or more like a catalyst to activate or to initiate many rigorous, meaningful collaboration between Southeast Asia, Taiwan, and other parts of the world. I wish this special symposium a very special and very inspiring one. Thank you very much. And I'd like to pass the time to our moderator, Professor Puji Lestari in ITB. Please.
Puji, Professor Puji, could you turn on your microphone? Yes.
Yeah, I'm sorry. Okay, good afternoon. I'm Puji Lestari. I'm from Institute of Technology Bandung, Indonesia. I'm attending this conference also from Indonesia. Today, I will be very honored for me to be a moderator for this session, and I will be moderator for 2 speakers. I have my first speaker, Dr. Somporn Chantara from Chiang Mai University, Thailand. She is currently a head of Environmental Science Research Center, an academic center for air pollution in northern Thailand. Her research work in the field of atmospheric chemistry, air pollution monitoring and assessment. She works also with various stakeholders on air pollution management. The most significant contribution in academic is air quality monitoring and assessment, focusing on air pollution sources and health impact based on chemical composition of atmospheric fine particles. Today, Dr. Somporn will present the project on the topic of pattern of size fraction, PM and PAHs in urban and rural area of northern Thailand. Dr. Somporn, the time is yours.
Thank you very much, Professor Puji, for your kind introduction. I have my video recorded. May I use that?
Yes.
From the secretary. Do you play that for me, or should I play it here? It's my pleasure to be invited as the speaker Good afternoon from Chiang Mai, Thailand to everyone. It's my pleasure to be invited as the speaker in the special symposium on aerosol and air pollution in Southeastern Asian countries in the 12th AAC 2022. And my name is CHANTARA from the Faculty of Science, Chiang Mai University. My presentation today entitled Patterns and Size-fractionated PMs and PAH in urban and rural areas of northern Thailand. May I start with the first slide? So as we know that biomass burning is the big issue in Southeast Asia. This picture shows the fire hotspots in Southeast Asia from January to April 2019. The patterns of the burning occur from the beginning of the year from the southern part, let's say from Cambodia and middle part of Thailand, and it shifted to the north. You can see more open burning in March and April in northern Thailand and Myanmar and Laos. If we use this data to plot the graph showing fire hotspot counts in the dry season, separating into individual countries, starting from Vietnam, Cambodia, Laos, Thailand, and Myanmar, we can see the pattern of the fire hotspots distribution. And the number of hotspots or the hotspot counts in Myanmar was the highest fraction. It's around 40%, followed by 20% in Thailand, Laos, and Cambodia. This is the data only from 1 year in the dry season of 2019. However, the pattern is quite similar every year, so we can use this data as the representative. And the factors that are affecting air pollution in northern Thailand can be divided into 3 main factors. The first one is the geography. Because this is the natural factor, we cannot change it. Most of the cities are located in the basin surrounded by the mountain. And the second factor is the meteorological factors. For example, calm wind, low rain, and temperature inversion during the dry season in our area. And the last factor is the anthropogenic factor. It is the source of the air pollution, for example, open burning and traffic emission. As I said, the geography of northern Thailand is quite unique. So this is the cross-section of the area. So you can see each province or each city has its own basin, starting from Mae Hong Son on the left-hand side, and Chiang Mai Lamphun Basin, which is the biggest basin in northern Thailand. This is the Lampang and Phra Basin. So each basin surrounded by high mountains. And this is the Chiang Mai Lamphun Basin. As I said, is the biggest basin in northern Thailand. And we have Intanon Mountain on the west direction. This is the highest mountain in northern Thailand. In Thailand as well. So altitude is around 2,500 meters above sea level. And when we talk about the particle size, let's say it can be divided into coarse particles or PM10, fine particles, PM2.5, and ultrafine particles or PM0.1. And in this study, we are focusing on various sizes of particles, including fine particles, as shown in this slide. Let's take a look at the data of daily PM2.5 concentration in Chiang Mai City, starting from the year 2011 up to now. So this graph shows the concentration of PM2.5 in each year. The problem occurs in the dry season. And each year we have the highest concentration varying based on the factors. For example, in 2015, on some day we have the concentration of PM 2.5 higher than 200 microgram per cubic meter, which is about 4 times higher than our standard, which is 50 microgram per cubic meter. Luckily, last year and this year we have more rain in the dry season, so the air pollution was not so bad comparing to the previous years. Based on our data, we use the SMPS instrument to measure the size of the particles in Chiang Mai atmosphere, and we found that about 60% of the particle size has the diameter less than 0.1 micron. So this is very interesting. This is the data from December last year. So that's why we are interested to study more properties of the fine particles in our atmosphere. According to our study in the project entitled Monitoring of Air Quality and Smoke Haze Situation in Upper Northern Thailand, we finished this study about last year. We did collect the samples from 2 study sites. One study site is in urban area of Chiang Mai. As you see in this map, the study site is surrounded by the red color, which is the community area. And our sampling site is actually at the meteorological office of Chiang Mai, nearby the international airport. And another sampling site is at the rural Chiang Dao rural Chiang Dao district, the north of Chiang Mai city. And the study site is surrounded by the yellow color here, which is agricultural area. And the green color is the forest area and mountainous area. We collected the samples using the 8-stage cascade impactor with the flow rate around 28 liters per minute. And this is the stage 0 from stage F. We divided the size of the particles based on the stage showing in this table. And these are the coarse particles. And the red colors representing the fine particles down to about 0.4 micron. And the backup filter collect the particle less than 0.4 micron. We collect these particles and related to the deposition potential of the particle size. For the coarse particle, PM10 up to 2 micron, they can penetrate to the nasal passages to primary bronchi. And for the fine particle, let's say from 2 micron to 0.4 micron, it can penetrate to respiratory bronchi to alveoli. And if the particle size less than 2.4 micron, they can penetrate further through the membrane and into the blood circular systems. This is our data. The PM concentrations during the smoke haze period comparing between urban Chiang Mai and rural Chiang Dao are shown in this slide. The different colors you see here representing different size of particles. And the black line here is the PM10 concentration obtained from the Pollution Control Department monitoring station nearby our sampling site. This is the table showing the concentrations of PM of the urban and rural areas. We see no differences between these two sampling sites in the coarse particles. But with the particles with the diameter less than 2.1 micron, we can see some differences. And the concentration in the rural area was higher than in the urban area. For each particle size in the phi mode. And also the total PMs can see the differences between the rural area and urban area. This graph shows the average concentration of SPM or size-fractionated PMs during the smoke haze period, comparing between urban and rural area. We found higher concentrations of PM in fine particles and in rural area higher than in urban area. The ratio of the particle less than 2.1 micron occupy around 61% in urban area, and they occupy around 69% in rural area. We analyzed the polycyclic aromatic hydrocarbons or PAH in our samples. According to the IARC or International Agency for Research on Cancer, they has grouped the carcinogenic compounds of these 16 PAH into two groups. The first group is carcinogenic to humans, which is benzoapyrene. And the second group can be divided into group 2A and group 2B, as shown in this slide. The total pH concentration in our samples during smoke haze season can be shown in this graph. This one is the urban concentration, and this is the rural concentration. Comparing between urban and rural areas, we can see that the total PAH concentration in rural area were higher than in urban area. So it's around 6 nanogram per cubic meter and 4 nanogram per cubic meter. The different colors here are representing individual PAH compound and comparing with the PM concentrations. So they were well correlated between the concentration of PAH and total PMs in both areas. And this slide shows the PAH profiles in fine and coarse particles. This one is the smoke haze period data, urban and rural information. So we found PAH in the fine particles more than in the coarse particle. And the dominant compound is the benzobifluorantine, both in rural and urban area during the smoke haze period. And during non-smoke haze period, we found some PAHs are found in the coarse particle or the green color here, while the fine particles also contain PAH in the high concentration. However, concentration of PAH during non-smoke haze period was much lower than in the smoke haze period. So the scale here is 2.5 and this one is only 0.16. And then we compare the ratios of 16 PAH between smoke haze and non-smoke haze period. And compare also between the sampling areas, urban and rural. From this slide, we see not much difference between urban and rural area for the coarse particles, but for the fine particles, we see more high molecular weight PAH, or the red color here, in the particle size between 2 to 3 micron, which is the same trend with 5 modes particle. But during the non-smoke period, we see some differences between urban and rural area in the cost mode, because we see low molecular weight of PAH more in rural area, while in urban area we found higher molecular weight of PAH in the PM samples. But for the 5 mode of PMs, the pattern of urban and rural area are the same. This is the size-fractionated PAH concentration in urban Chiang Mai. So we found higher concentration of PAH in the 5 mode of PM, both in smoke haze and non-smoke haze periods. And the dominant compound of PAH found in smoke haze period is benzo-B-fluorantine. So this one is the biomass combustion emission tracer. But during the non-smoke haze period, we found these 3 compounds or more than the others. So during non-smoke haze period, the PAH are emitted from urban traffic and local activities. And these 3 compounds are markers of traffic-related emission. During smoke haze period and non-smoke haze period in rural sampling site, we found similar pattern as shown in the urban area, and the dominant compound is still is still BBF, which is the biomass burning emission tracer. And during the non-smoke haze period, we still found these 3 compounds as we found in the urban area. When we do the correlations between SPMs and total PAH, we found that for the cost PMs, the correlation between cost PM and PAH is always low to moderate. But for the 5 PMs, we found strong correlations between PMs and PAH. This can be suggested that they have the same origins in case of 5 PMs and total PAH. The particle size reduction will enhance the mass of PAH absorbed on PM surface. So that's why we found higher concentrations of PAH in 5 PMs rather than in coarse PMs. And this slide shows the distribution histogram of SPM's concentration. The graph is plotted between dC by d log dP and the particle diameter. When the dC is the average concentrations of SPM and the dP is the average diameter of each particle size. This is the data from smoke haze season. We found bimodal distribution both in urban and rural area. And the dominant peak was found in the finest particle from 0.4 to 0.6 micron. And the small peak was found in the cosmos between from 5.8 to 4.7 micron. So that from the distribution histograms, it can be concluded that the variation characteristic of particle size distribution were mainly due to the different formation mechanism of PMs. And the fine particles are mainly attributed to emission from combustion process and converted into the ultrafine particles through the accumulation mechanism and condensation of vapor species. On the other hand, the coarse particles are mainly formed from incomplete combustion process. It can be formed due to the resuspension of surface dust or the soil particles by wind direction. And the similar PM size distribution pattern in both urban and rural atmospheres during the smoke haze season indicated that particles are emitted from the same origin, which is biomass burning source. For the source distribution of total PAH during smoke haze period, comparing between urban and rural site, is show the same pattern, which is bimodal. But during the non-smoke haze period, in the urban area, is show bimodal. On the other hand, during in the rural area, it's show unimodal. This is due to the source during the non-smoke haze period, which is not the same as smoke haze period. In this case, the major source is biomass burning, but during the non-smoke haze period, the source is more specific with the area. After we got the concentration of PM and PAH, then we calculate for the toxicity equivalent concentrations or TEQ of PAH from this equation. So we have to use the concentration of individual PAH and the constant values TEF. The TEQ can be identified based on the TEF, which is the toxic equivalent factors of each group of PAH compounds. So this one is referred to Nisbet and Lagon. After calculation, we got the data and can be plotted as shown in this graph. During the smoke haze season, we found that the TEQ values are high in the 5 PMs. And the TEQ values of the 5 PMs are higher in rural area than in urban area. So the green one is higher than the red one. And during the non-smoke haze season, we found TEQ values are high in 5 PMs. We found some differences that TEQ values of 5 PMs are higher in urban area than in rural area, which is opposite with during the smoke haze season. So the red one is higher than the green one in case of the TEQ values. After we got the TEQ values, we calculate further to get the ICR or inhalation cancer risk. ICR can be calculated using the TEQ value multiplied with the IUR, benzoapyrene. IUR-BAP is the inhalation unit risk defined as the risk of cancer from a lifetime, which is about 70 years, inhalation of unit mass of benzoapyrene. WHO recommended the IUR-BAP value at the 0.087 cubic meter per microgram. And the ICR calculation is based on the US EPA. ICR values are between 10 power minus 6, which is the lower bound zero risk, and 10 power minus 4, which is the high potential health risk. And Chiang Mai population is around 1.7 million, and the life expectancy is around 70 years. From that calculation, we get the data as plot in this graph. The ICR value were plot based on the particle size, and we found increasing values of ICR from coarse particles to the fine particles. This also compare between Chiang Mai urban area and Chiang Dao rural area. So we found higher risk in small size of PMs or PM1 comparing to the coarse particles. And during non-smokeless period, the same trend was also found, but with lower value in case of ICR. And when we compare between rural and urban area during the smokeless period, the red color here is the urban value and the green is the rural area. We found urban area has the medium risk during the smokeless period, but rural area has high risk. How about during non-smokeless period? It was found opposite. The urban area has the medium risk, while the rural area has low to medium risk during the non-smokeless period. This is because the source of the non-smokeless period is not the same as smokeless period. In urban area, we still have high traffic congestion. So that's why the risk of ICR is higher than in the rural area. Now come to the conclusion. The 5 PMs or the PM with the diameter of 2 micron to 0.4 micron accounted for 62 to 68% in both urban and rural atmospheres. And a group of finest particles from 0.4 to 0.6 micron was the largest portion found in this study. During the smokeless season, high PAH concentrations were found at the rural area due to intensive open burning. Conversely, during non-smokeless season, traffic emission is dominated in urban area, as mentioned earlier. The PAH with higher carcinogenicity, or 5 to 6 strings of PAH, were likely to concentrate in 5 PMs. The patterns of size distribution of SPMs and PAH were similar, which is bimodal. And the patterns of size distribution of PAH were different between urban and rural areas due to different emission sources during non-smoking season. This is the reference of my presentation. So we already published this work in the environmental pollution. Thank you for your kind attention. This is my students and staff. If you have any question, we can discuss more in the discussion part. Thank you very much.
Thank you, Dr. Somporn. So I will open for the few questions here. So if you have any question from the floor or from the room, please raise your hand or you directly talk and address your question to Dr. Somporn. This is very interesting presentation. So it's talking about the size distribution during non-haze and haze periods, and also PAHs in the fraction in Chiang Mai. So I open the question. Is there any question?
Yes, yeah, we have.
Yes, please.
Hi, my name is Tochi, from National Taiwan University, and thanks for a wonderful presentation. And so far, I really impressed for your work. And also because there is only one slide talking about the SMPS data. Actually, we do a lot of measurement of particle size distribution in Taiwan for like several years, and I'm glad. I mean, in Thailand, right now you also have some SMPS data. Then we probably can make a comparison later. But you say one thing is like I think the number I don't remember exactly. Probably 60% particles reside in PM1 or something, and that is in terms of number or mass, because I guess is should be in terms of volume or probably first. Because I think if in terms of number it should be more. That is from my guess. But if you want to convert to the mass using SMPS data, then there is some assumption you should make like density, which is very difficult to retrieve sometimes. So that is first. I'm just curious or if you prepare any further data about SMPS like particle size or typical size distribution like this. Okay, thanks. Thanks for the presentation.
Thank you, TC, for your comment. Yeah, of course, it's very interesting to see that maybe in the future we can compare our data between Thailand and Taiwan. So you asked about the SMPS measurement of my presentation. So may I share my screen? Yes, I show one slide on the measurement of the particle size using SMPS. This one, right? Yeah. So and I mentioned that around 60% of the particle size belong to the PM 0.1. This one is only 1 day measurement that we conduct on the 8th of December last year. And we calculate it back to the percent comparing to the various size of particles that we have. But in detail, I might need to look again whether it's a number or it's really a mass. So thank you for raise this question. So maybe you can also give me some advice about how to make sure whether that's correct data that we have. However, it's quite a limit information that we have. So we just got this instrument from one of the company in Bangkok to measure for a short time. So maybe next year we will try this again, and I hope that I can consult you in more detail.
Yeah, I think that exchange some ideas really console me. Sorry, probably I do not take a clear look during your presentation. I think yes, your data is in terms of particle number. I believe so because the shape and the size like this. Just the y-axis probably need to be more careful. Then but probably I think later on, yeah, if you have more data, then we can see what we can do. Maybe compare with the other countries in Southeast Asia. Okay, thanks.
Sure, thank you.
Thank you. Any more questions from the floor or from online participants? Any question? No question from the Let me see if anyone. No question. Maybe I will have
Yes,
just.
hello.
Yeah. Oh, yes.
Yes.
Yes, please.
Yes. I have one question. Is Professor Songdong. Because there's biomass burning is important problem. Maybe it's a serious problems in the Thailand or Southeast Asia, and have any policies or restricted policies released from the government to prevent this biomass burning occurred. So this recently, yes.
Thank you, Peter. So you asked about the government policy or?
Yeah, yes.
Okay, yes.
Yes.
Okay.
Yeah.
Actually, the problem is quite serious in northern Thailand, and the government has also implemented the policy that so-called the zero burning policy. So it means during the dry season, we are not allowed to burn anything for about 2 months or 60 days. They implemented this policy for more than 3 years already, but it's not quite successful. So that's why we are now trying to adapt or change the behavior by also implementing the new application. We call it Fire D, or it means the biomass burning management. So instead of biomass burning control, 0% burning. So we will allow the burning sometimes when the ventilation is good enough. We use the model to predict the air quality in advance to see whether the air ventilation is good. So then we will allow just only in some area that they already have registered in the system to burn their biomass in the area. So this is just a compromising policy, and I think we might go to the better direction now. Yeah.
Okay, thank you.
Okay, thank you for the questions. I think I just have last question or maybe comment on your presentation. I think it is very, very good, very comprehensive presentation. And I have a little bit question actually about the PAHs. As we know that PAHs can be some PAHs with low molecular weight. Sometimes it's exists in the gas phase. So some of them are especially for higher molecular weight, usually it's in the particle phase. So are you concerning of this gas phase as well, or measuring the gas phase so that you could combine and see within the distribution within the particle and gas phase distribution of PAHs? Because I think it's very important as well. And then my second concern is the temperatures. As I just mentioned, that PAHs can be both phase, gas and particulate, then PAH is also temperature is also very important. So did you also measure temperature during the sampling times and check whether they have any impact to your concentration in the particulate matter with the temperature correlation, something like that?
Thanks for the questions. I think it's very good points, because the gas phase of PAH actually is very important as well. But in this work, we more consider on the particulate phase. We also measure the gas phase of PAH in another project. We also have some data to show that the gas phase of PAH actually have higher concentration, particularly in the low molecular weight of PAH. Yes, that is quite certain. Yeah. About the temperature during the measurement, because our experiment is mostly in the dry season and the ambient temperature is quite high, so sometimes it's reached to 40 degrees Celsius. So this is quite common in our area, right? So it is, we record the temperature. We use the data from the meteorological office, And we found that during our sampling is quite high temperature in the dry season, but during non-haze period, it's the rainy season, the temperature is lower, but sometimes it's also reach 30 degrees Celsius. So this is quite a common behavior of the Southeast Asia. So I think it's quite a condition for our study as well. I hope you get the answers.
Yeah, I get the answer. Okay, I think I will close this session because I think it's time. And if you have all still question to Dr. Somporn, I think at the end of this session they will have a Q&A again for all the groups. So please let us know in the end of this session if you all still have a question.